Now, before we can begin with our structural design, I'm going to delve into structural steel design and I will talk about reinforced concrete. To design any structure, we first have to deal with its loading. Now, the aspect of loading is a critical aspect because it determines how structures bear the weight of various forces. In this case, I will try to discuss as many loads as I can. Now, there are mainly two types of loads. The first one being the permanent load. Now I'm going to denote the permanent load with DN. Now the permanent loads are also called dead loads. Because permanent loads are also called dead loads, I will use DN here to denote my permanent load. Remember that the N means nominal, which means that my loads are unfactored. They are not, we have not included the factor of safety yet. Remember, when you design, you want to design for a larger force than the actual force that is being experienced by the structure, so that you can leave some factor of safety in your design. Now we have permanent load and we have imposed loads. Now imposed load means basically the loads can move about or change their orientation. You can even remove them or put them back at any time. And in this module, we will discuss the live loads and the wind load. Let's first talk about the permanent load. As I've already mentioned, with permanent loads, you will have dead loads, or you will have the self weight of a structure. Let me also include that they are also called static loads. These permanent loads, they are the inherent and constant weights of the structural elements and materials that comprise a building or a structure. So they are part of the structure itself. These loads encompass the weight of everything that remains stationary within the structure, from walls, floors, roofs, and columns. Even the finishes in the structure, such as a plaster, the paint, or even the building's own self-weight. Now, suppose we have an element here made from concrete, or maybe another element here made from steel. Now I will put a roller, just for explanation purposes. Now this reinforced concrete or the structural steel that you will be using, they will have gravity acting on them. A structure does not just float in the air, so gravity is pulling them down, meaning that it will experience weight, and the weight is the force that gravity is exerting on a material. Now all matter have mass, therefore all matter will experience weight. Now because of this weight, this self weight of the structure is called a permanent load because it's inherent and is constant throughout the life of the structure. Now dead loads are ever present and they play a fundamental role in the overall structural integrity of a building. Now let's just show my weight here. The self weight of the structure is shown by a distributed load because each point in this element has mass, therefore is experiencing weight. So I will have weight dN and I will have weight dN. Here I have my reinforced concrete and here I'm using structural steel. Now beyond the structure, finishes like ceilings, wall cladding, floor covering, and even fixed furniture and equipment all contribute to dead load. So in essence, dead loads encompass all the static unchanging weight that a structure has to support. Now, calculating dead loads involves quantifying the weight of each component and material accurately. Now, for instance, determining the weight of a structural steel member. Example, this one. It involves considering their dimensions and the material's density. Now, with imposed loads, they are also called the live loads. You can also call them the variable variable loads. You can see dead loads, live loads, variable static loads. Now, these live loads are the transient forces that structures experience due to the presence of people, furniture, equipment, and other movable elements. Now, with permanent load, we spoke about permanent structures like floors, we spoke about roofs, we spoke about walls and columns that all contribute to the dead loads, and many other things like wall cladding, floor coverings that all contribute to the permanent load. Now, imposed loads come from movable elements. Unlike dead loads, which are constant and inherent to the structure, live loads are dynamic and fluctuate as occupancy and usage change. So live loads can vary significantly based on the function of a space and the activities conducted within it. For instance, the live load in a residential area would be different from that of a concert hall, gymnasium, or office space. Different activities lead to varying loads that structures must accommodate. So calculating these live loads involve determining the maximum expected load based on the occupancy of or the function of the space. With dead loads, you will need to go to your standards to consider the density of the material that you are using, the dimensions of your members. Here you have to consider all things, including movement that will take place on your structure. So building codes and standards provide guidelines for estimating live loads for different types of spaces. These guidelines consider factors like occupancy, use, and expected load per square meter. So as an engineer, you must ensure that structures are designed to withstand these maximum live loads safely. Just like the dead loads, safety is paramount when considering live loads. Hence, during this module, we'll also talk about the safety factors, because these live loads are typically amplified by safety factors to account for uncertainties and variations, and these factors ensure that structures can handle unexpected loads and changes in usage. Now, the combined effect of dead loads and live loads and other forces create what we call design loads. So we'll discuss this, as these loads guide engineers in dimensioning structural elements. Just to cap off this video, let's just make some simple idealized examples. Let's say I have a beam, and in this case my beam is made from reinforced concrete. Now I have a support there and I have another support there. Now my member is experiencing some dead load. I'll call it DN, but also it is experiencing some live load. I will call it LN. We said that live loads we are going to use LN. Suppose that my dead load is equal to 12 kilonewtons per meter, since it's a distributed load, and also my live load is equal to 10 kilonewtons per meter. How do we calculate the design load on the member? What we are going to do is to take the dead load. We are going to find the dead load by taking a factor of the dead load. Now, this dead load will multiply it by 1.2 as given by the guidelines. Now, in this instance, I'm using South African national standards, and to my factor for a dead load will be 1.2. So I will have 14.4 kilonewtons per meter. Now, my units of measurement do not change because I only factored it. Now, My variable load, however, I will multiply it by 1.6. Now 1.6 multiplied by 10 will be 16 kilonewtons per meter. Now to find my design load, it will just be the combination of the dead load and the live load. So my design load, denoted by W in this case, will be 14.4 kilonewtons per meter plus 16 kilonewtons per meter, which all adds up to 29.4 kilonewtons per meter. Now you can see that the dead load was 12, the live load was 10 kilonewtons per meter, but the design load that I'm going to use will be factored. It will be larger than the original dead load, so that we can account for uncertainties and variation. This is how we make sure that the structure is safe. Now, this is a more complicated example, but we are not designing the entire floor slab. What I just want us to do is find the loading on the slab. Now the question says calculate the loading on the slab of the following building. Now we are given that the mass density of reinforced concrete is 24 kilonewtons per meter square. Now this value, you can find it in the South African national standard. Now each of the guideline books have its own purpose, and the SANS 101602 on table A1 you will find the different mass densities for different material. Now you are also given that the mass density of screed is equal to 22 kilonewtons per cubic meter. What we also have here is the thickness of the slab. You are told that it is 220 millimeters. That is the thickness of the slab. Now the screed is 50 millimeters, and also the ceiling and surfaces give you 0.5 kilonewtons per meter squared. The first thing you're gonna do is to calculate the dead load. Now remember that you will have the dead load and you will also have the live load. Now the dead load is the permanent load, the unvariable static load that is unchanging, including the self-weight of the materials. Now in this instance, the material that we used is reinforced concrete, meaning that our reinforced concrete includes concrete and some structural steel inside for tension. Now the dead load, let's say, is given by GK, but to be consistent, let me use DN. So how do we find the dead load? First of all, we have the mass density. Remember, to find the dead load, you must consider the dimensions of the structure and the density of the structure. So the density is given, and we know the dimension of the structure because we know the thickness of the slab. So we will take the 220 millimeter slab and we will multiply it by the mass density of the reinforced concrete, which is equal to 24 kilonewtons per cubic meter. Now that will give you 5.28 kilonewtons per meter squared. Now you just convert this to meters, which is divide by 1000 and multiply by 24. Now this meters will cancel 1 meter and you will be left with square meter instead of cubic meter. We also know the dimensions of the screed. It's hard to explain what screed is, but once you build a floor or you build a wall, and some places will be uneven, and you use screed to level out your floor or your walls. Basically, you use it to level out your concrete sub-base. Now, in this instant, we are given 50 millimeters of screed. Now, also, we are going to take that and multiply the dimensions by the density. Now, the mass density for screed is 22 kilonewtons per cubic meter. Now 50 millimeters times 22 will give you 1.1 kilonewtons per meter squared. Now, what else contributes to the dead load? We also have the ceilings and services that are all permanent on the structure. Therefore, they are dead loads. So from the ceiling and services, we will have 0.5 kilonewtons per meter squared. So when you take all these and you add them together, you will find that your dead load is equal to 6.88 kilonewtons per meter squared. So this is your permanent load. That includes the self-weight that we find on the slab and the screed. And now that we have the dead load, we can calculate the live load. The live load, I will denote it with Ln. So this one we are not given in the question, but if you go to the South African National Standards, SANS 10160-2 in table 1. Now table 1 will give you all the live loads, the general live loads for different types of buildings. Now in this building, we have not specified what type of building we are working with here. So we're just gonna take the live load for a general office building. The live load for a general office building is given by 2.5 kilonewtons per meter squared. The live load from the movable partitions, it is equal to 1 kilonewtons per meter squared. Now when you add these two together, you will find that your live load is equal to 3.5 kilonewtons per meter squared. So now we have the live load and we have the dead load. So we can calculate the design load that is going to be used in the design of this slab. So now we go to load combinations. My design load will be given by 1.2 dead load plus 1.6 live load. Now these factors are important. I didn't just make this up, and you don't use this for every building or structure that you make. You have to follow your national standards so that you find which factors to use. In this case, I use the South African National Standards, the same document that I have been using so far, and I got them from table 3. Now, my design load, I can denote it by W. Now, it is going to be 1.2 multiplied by my dead load is equal to 6.88 plus 1.6. My live load is equal to 3.5. And this will give me 13.86 kilonewtons per meter squared. Now, this 13.86 kilonewtons per meter squared is what we are going to design for. You notice that this loading, it's larger than the original dead load and live load combined to allow for uncertainties. Now, a general structure of this slab will look like something like this, and then you will have your loading, your design load on this, and then you can calculate for the support reactions and then design for your member.